Hi, I'm David Millard, and along with my co-authors Heiden, Erwin Coumans, Yizhou Sheng, and Gaurav Sukhatme, I would like to present NeuralSim, a study on augmenting differentiable simulators with neural networks. In this work, we aim to model dynamical systems accurately while ensuring that our approximation generalizes to different behaviors exhibited by the actual mechanism we try to model. As such, we treat the model as a function that predicts the evolution of the system's state, which means it calculates the next state given the current system state. Several techniques have been proposed in the rich area of system identification, where analytical models are updated from real-world measurements. Recently, physics engines have been leveraged as complex models of the world, for which it is crucial to reduce the gap to the real system in order for controllers created in simulation to transfer to the real world. The parameters of these models can be estimated from data using traditional analytical system identification techniques. With the advent of expressive deep neural networks, behavior can be learned without a physical model directly from data. These directly learned models often fail to generalize to accurate predictions outside of data shown at training time. Recently, residual physics models have been proposed. These combine the two aforementioned approaches to correct a total unmodeled error from a physics engine with a neural network. We present hybrid simulation, a more specific, interpretable, and sample-efficient technique of embedding neural networks directly inside a differentiable physics engine to jointly optimize interpretable parameters and specific data-driven estimators. At the core of our approach is the idea of a neural scalar. By assigning a name to a physical quantity inside a simulator, we can identify this quantity as an input or output to a neural network, specified via a neural blueprint. When a quantity is evaluated, the outputs from any dependent neural networks are computed and added to the analytical physics model. For some problems, equations of motion are unknown or non-existent, so the neural network comprises the entirety of the prediction. For other problems, the neural network serves as an internal residual error correction term against a known equation. The neural scalars approach supports both modeling techniques and is configurable per network. Physical equations of motion are often highly nonlinear, leading to many local minima during hybrid training. We leverage global optimization techniques like basin hopping. In the experiment shown on the left, the link lengths of a double pendulum are inferred from a trajectory of joint positions. As a system identification objective, we used the common L2 error, which we evaluated between the simulated trajectory given the parameters and the ground truth trajectory, which in this case has been simulated from a double pendulum with link lengths of 3 and 4 meters. By minimizing this error between the simulated and real trajectories, local optimizers, such as LBFGS, shown on the left, converge to parameters that are often far from the actual solution. The heat map visualizes for different initial parameter guesses for the two link lengths the difference between the parameters found by the LBFGS optimizer and the true solution. When we apply basin hopping, which implements a random restart strategy and uses a local optimizer internally, we see on the right that no matter from which parameter setting we start the optimizer, we will always converge to the true link lengths in this experiment. Besides basin hopping, we leverage the various other global optimization techniques from the PAGMO library. PAGMO provides population-based optimization algorithms that leverage parallelization and gradient-based optimization to find a variety of solution candidates which are continuously recombined and mutated to approach a globally optimal solution. Due to the high inductive bias of physical equations of motion, our approach of hybrid simulation shows significant improvements in accuracy and data efficiency compared to other deep learning approaches. Here, we show that hybrid simulation techniques can learn accurate dynamics predictions on a reserved test set given very few sample trajectories. A more common deep learning technique, here a feed-forward network, requires many more varied trajectories to generalize to correct behavior on the reserved test set. There are many quantities involved in a physics simulator, and it can be difficult to know which quantities are relevant for a given data set or physical effect. At the same time, the neural augmentation must only be applied where it is strictly necessary, so as not to reduce the generalizability and predictive accuracy of the analytical model. We use techniques from sparse regression to aid in identifying the proper quantities. By applying a lasso loss to the input layer of each network and a ridge regression to the higher layers, we demonstrate discovery of the importance of velocity parameters for predicting frictional forces. Here, you can see the progression of the weights of a sparse network while a damped double pendulum is identified. By using the sparse lasso loss, the connection between joint velocities and their respective joint forces is discovered, which corresponds to the joint friction in the double pendulum equations of motion. Our differentiable simulator and neural network library, the tiny differentiable simulator, is written in C++ and is agnostic to the choice of linear algebra and automatic differentiation library. In the course of this work, we benchmarked many automatic differentiation approaches. We found that automatic code generation techniques yield orders of magnitude improvements in computation speed. These comprehensive benchmark results are further presented in our paper. An exemplar problem that our approach can solve is a golf ball moving through an unknown medium after an initial impulse. Despite our rigid body simulator not having a viscous friction model, by inserting a neural network, we are able to accurately predict the passive forces generated by the medium. This example also showcases a primary advantage of our approach. The predicted quantities are interpretable as forces rather than as an opaque error correction term. A more complex example predicts the movement of a swimming robot through a viscous fluid medium. Here, the passive forces are also a function of the position and angle of incidence of each link relative to the velocity in the medium. Despite our simulator not implementing this viscous friction model, we accurately predict the motion of the swimmer, where analytical system identification fails. In our next experiment, we leverage the planar pushing dataset from the MIT MCube lab. The dataset contains trajectories of objects with different shapes being pushed by a robot with a cylindrical tip attached to its end effector. Our goal is to learn the delicate friction model that is at play while the metallic shape is pushed over various surface materials. As shown on the left, our analytical force-based contact model exhibits a noticeable sim-to-real gap to the actual behavior shown in green. We sample contact points on the 2D footprint of each shape over a uniform grid. We augment the friction model by a neural network that operates on each of these points. Through the uniform sampling of contact points, we aim to generalize to new shapes, while the neural network models the friction response inherent to the interaction of the ground and object materials. We demonstrate the performance of our hybrid approach, where the simulator is augmented by a neural network, against the purely analytical model and two entirely data-driven approaches, a feed-forward neural network and a long short-term memory network. As can be seen in the top row, our approach achieves a significantly smaller deviation from the real pushing motion, shown in green, compared to these baselines. Since our augmentation is to individual elements in the contact point grid, our learned model generalizes to different geometries without retraining. In our last experiment, we investigate the combination of analytical and data-driven models for quadruped locomotion control. We replace a quadratic programming solver by a neural network that is used inside a Model-Predictive Controller. The network is trained via supervised learning from a solution dataset of the QP solver. This approach yields significant computational benefits. We observe a 10 times speedup when the neural network is used in place of the QP solver on a real Unitree A1 quadruped robot. As shown here in simulation, the neural network-based QP solver on the left yields closely matching motions to its counterpart shown on the right. Thank you for your interest in our work. Please find videos and supplementary materials at our project website. You may find our C++ implementation at the linked Tiny Differentiable Simulator GitHub repo.